بسم الله الرحمن الرحيم. اليوم راح نبلش في chapter 7 اللي بيتعلق في الكنترولر ديزاين based on pole placement technique. وهذا الشابتر هو عبارة عن الكور اوف ذيس كورس، هو عبارة عن أهم إشي في الكورس اللي بين يدينا اللي بيتعلق في الكنترولر ديزاين بناء على البول بليسمنت تكنيكس. في البداية حابين نعمل زي مقارنة بين البول بليسمنت ابروتش اللي بيمر معنا هسه بالشابتر الحالي اللي هو الديزاين اوف كنترولر في الستيت سبيس، مقارنة بينه وبين الكورس اللي أخذناه في الأوتوماتيك كنترول سيستم. فبالتالي في عنا هون الديفرنسز بين البول بليسمنت تكنيك والكونفنشنال ديزاين اللي أخذناه في الأوتوماتيك كنترول كورس اللي مبني على الليد أور لاج compensators based on root locus or body plot. كلاهما lead or lag سواء كان في time domain root locus أو بالفريكونسي دومين في البودي بلوت. فبالتالي هون احنا قاعدين بنقارن بين البول بليسمنت في الستيت سبيس اللي هو الكرنت والكونفنشنال اللي هو ابروتش اللي بالاوتوماتيك كنترول كورس اللي هو ليد اور لاج ديزاين. فاول حسنه من حسنات البول بليسمنت انه في البول بليسمنت نعمل سيلكشن للديزير لوكيشنز للديزيرد لوكيشن فور اول كلوز لوب بولز. لو كان مثلا عندنا سيستم فيفث اوردر بنعمل بليسمنت وبنعمل تحديد لمواقع الكلوز لوب بولز او الروتس تبعت الكاركترستيك ايكويشن كلياتهم. all of the closed loop poles will be determined, will be specified سواء كان dominant or non-dominant poles. بينما في الconventional course if you remember كان الديزاين مبني تبعنا على حركتين. أول إشي إنه في عندي a selection of a pair of dominant closed loop poles only. الشغلة الثانية كان مبني على أساس عملية reshaping بتتم للروت لوكس في التايم دومين أو للبودي بلوت في الفريكونسي دومين. فأول حسنة إنه في البول بليسمنت نعمل سيلكشن أو بليسمنت أو تحديد أو زراعة للروتس تبعت الكاركترستيك ايكويشن أو البولز الديزيرد كلوز لوب بولز بالمواقع اللي بدنا اياها لكل البولز، مش عباره عن تو بولز. بينما في الكونفنشنال ابروتش في الليد اور لاج اوكي كنا بس نحدد بير اوف دومينانت والبقيه على مبدا يعني ترايل اند ايرور. اوكي ممكن تزبط وممكن ما تزبط. والبير اوف دومينانت كلوز لوب بولز اللي كنا نختارهن في الكونفنشنال ابروتش كان بناء على انه في عندي ديزيرد دامبينج ريشيو وديزيرد اوميجا ان، منها نطلع الاس دي 1 و 2. اوكي الفرق الثاني انه الديزاين تبعنا في البول بليسمنت مبني على اساس نعمل سيلكشن لماتريكس راح نشوفها بعد شوي اسمها الجين ستيت فيدباك جين ماتريكس، وهاي بنعملها تحديد بنختارها بنحدد الفاليوز تبعاتها. اوكي وهاي شرطها حتى نقدر نحددها ونقدر نعمل كنترولر ديزاين لازم السيستم يكون كومبليتلي ستيت كنترولابل. وبالتالي اللي اخذناه بالشابتر البريفيوس شابتر عن الكومبليتلي ستيت كنترولابل وكومبليتلي ستيت اوبزرفبل، هون بالشابتر هذا راح يتم استخدامه. فالديزاين مبني على اساس انه نختار جين ماتريكس ستيت فيدباك جين ماتريكس كي، وهاي شرطها الكونديشن فور ذا design to be successful انه يكون السيستم the system should be completely state controllable. بينما في الconventional approach مبنية على اساس انه بنضيف poles and zeros to the plant or the original system، وهذا البولز او زيروز بيعمل عملية reshaping يا اما للروت لوكس او للبوتو بلوت. اوكي هسا الفرق الثالث انه في حالة البول بليسمنت الاوردر of the original system will be the same. It will not increase by the addition of the controller. بينما في الconventional system اوكي في البول في الليد لاج كان السيستم اذا بنضيف ليد اور لاج بيزيد بمقدار 1، واذا بنضيف ليد اند لاج بيزيد بمقدار 2، الا اذا كان في عندي بول بليسمنت، وهاي البول بليسمنت عاده نحن بنحاول نستثنيها او نبعد عنها. اوكي الفرق الرابع انه البول بليسمنت ديزاين ابروتش بيحتوي على حالتين، يا اما ان يكون كل ستيت فاريبلز they are available for direct measurement، او اذا part of them they are not available for direct measurement انه يكون في عندي السيستم completely state observable، وبالتالي لابد ما انه نشمل بعمليه الديزاين تبعنا انه نعمل state observer حتى يعمل estimation للستيتس من الاوتبوت، وهذا اللي حكيناه في الشابتر الماضي. بينما في الكونفنشنال ابروتش ما في عندنا اي requirements على الستيت variables of the original system. اوكي، هسا خلينا نشوف الديزاين اوف فول ستيت فيدباك كنترولر. اوكي، هون في عندنا ستيت سبيس ريبريزنتيشن لسيستم بتكون من اللي هي الماتريسيز A B C D. اوكي، والانبوت اللي عندنا اللي هو اليو، وهون بنفترض انه اليو اللي هي الكنترول سيجنال في حاله اللي هي الستيت فيدباك كنترولر. اوكي، اليو is equal to minus kx. اليو is equal to minus kx. So we take the state variables and we multiply each state variable by a certain gain, like x1 by k1, x2 by k2, x3 by k3 till xn by xn. So we multiply this these states by a certain k matrix, and k matrix for multi-input it's m by n, and for single input it's 1 by n. Okay, so k matrix is the state feedback gain matrix. Okay, if we take this control signal u and substitute it in the first equation here, okay, what we will get? We will get x dot is equal to a minus bk multiplied by x. Okay, and this is very similar to the discussion that we have in chapter 5. If you remember chapter 5, it was about zero input response and zero state response and the response and stability of state space models. Okay, and I want to remind you with chapter 5. I have taken one page that we have discussed previously just as a way to excite your memory. So if you assume LTI, this is exactly from chapter 5. I did not add anything. This is from chapter 5. Okay, and those equations, they are existing in chapter 5. So x dot is equal to ax plus bu, and we apply the Laplace transform on this equation and perform certain manipulations, and finally we will get this equation. And this equation, okay, it consists, as we mentioned, of from two parts, this part and this part. Okay, this part is the zero state response and this part is the zero input response. Okay, so here the zero input response is the first part, while the zero state response is the second part, and the overall or the total is the summation of both of them. Okay, so we are interested in the zero input response. In case of zero input response, u will be 0. This u, okay, in case of zero input response, this u will be 0. So what will be the state equation? This term will be cancelled and we will have only this term, x dot is equal to ax. And this is what's mentioned here. For zero input response, the state equation become of this form. And if you remember, this, the solution to this is e to the power atx of 0. Okay, and it will be also this solution from this equation. So we can equate both of them here. We can equate both of them, and this we have taken phi of t, we call it state transition matrix, is equal e to the power at Laplace inverse si minus a inverse. And if you remember how to calculate the inverse, it's the adjoint divided by the determinant of this si minus a. Okay, so for stability, this si minus a, the roots of this si minus a, which are the eigenvalues of matrix A, we have discussed this before, should be all in the left half side of S plane. So for stability, all the eigenvalues of A matrix, they should be in the left hand side of S plane. And for our system, as I mentioned, x dot is equal to ax, we have the solution x of t, okay, is equal to e to the power a t x of 0. Okay, so here a and whatever the multiplier here, it will appear as an exponent. So this is what we need in this chapter. Okay, so in this chapter we reached to this equation: x dot is equal to a minus bk x of t. And now instead of a in the previous chapter, we have a minus bk in this chapter. We will replace, and if we replace a minus bk with this, okay, then we will get this equation of the solution x of t will be e to the power minus pk x of 0, and for stability and the transient characteristics, they are determined and controlled by the eigenvalues of a minus bk. There, previously it was the eigenvalues of a matrix. While here it's a minus bk. Why? Because we have assumed that u is equal to minus kx. Okay, and in order to perform this Pauli placement arbitrary, so that you can select the desired closed loop poles anywhere in the left half side of a plane, there is a necessary and sufficient condition that the system should be completely state controllable. Okay, so what are the conditions, or the conditions that we discussed just now? They are based on assumptions. Number one, all of the states, they are available for feedback, and the control signal is unconstrained. And this is the concept of controllability. If you remember, the concept of controllability in that previous chapter is to transfer all states from an initial value to any final value over finite interval of time using unbounded u of t. So u of t is unconstrained or unbounded, and all of the states should be available for feedback. If they are not available for feedback, then we should use an observer. And this is the block diagram of the system. Here we have x dot. Okay, here we have x dot. So if we see, this is x multiplied by a, so here it will be ax, and here x multiplied by k, and here this u is equal, so this means that minus kx, and we multiply this by b. So what will be the final answer? X dot is equal to ax plus bu, and u is equal to this value. So this is our model for our system that we assume in the previous page. Okay. Now, the eigenvalues of the matrix A minus bk, we call it desired closed loop poles. Eigenvalues of the matrix A minus bk, they are the desired closed loop poles that we want to place the poles at this location. Okay, so if all of those desired, they are in the left, then the system is stable, and x of t, due to initial states, will be 0. And if the system is not completely state controllable, but it's stabilizable, we discussed this concept, then we can make the system stable, the entire system stable. How? By placing the closed loop poles at the desired location for the q controllable states, and the remaining states which are uncontrollable, they are already stable, so the entire system will be stable. And this we have discussed before in the concept of stabilizability. Okay, and for this system, if we notice that the closed loop system has no input, because we have assumed that u is equal to 0, and we are considering these zero input response. So the objective of this system is that the output should be 0. Okay, and the reference is assumed 0, or the input is assumed to be 0. So how can we determine the state feedback, okay, and in the following sections we will cover for single input system. We will cover the procedures to determine the value of K, okay, state feedback for single input systems. Okay, so the first method is using transformation. Okay, so the state feedback gain matrix K, it forces the eigenvalues of the system to be A minus BK, which are the desired poles. So we set the desired poles, we place the desired poles from PP1, PP2 till PPN. These are the desired location that we want to design our controller to set those new desired values of the closed loop poles. So we set those PPs from PP1 to PPN according to our specifications. Okay, and the K value will force the old system, which has an its eigenvalues of the eigenmatrix A, and it will be the eigenvalues of the new system will be the roots of, or the eigenvalues of A minus BK. So we will check in the second step, we will check the controllability of this system. And if system is complete state controllable, we will proceed. If not complete state controllable, then we will stop. We cannot determine K. Okay, the third step is that we will find the characteristic equation of the original system. Okay, Si minus A determinant, and it will be an nth order. And from that nth order, we determine all of the coefficients A naught till An minus 1. And in this step, we perform similarity transformation. In this step, we perform similarity transformation. Okay, we find the T matrix as we discussed in the similarity transformation. This is QC and this is W. I will not discuss. So we perform similarity transformation that convert the original system into CCF. Okay. So we find this T matrix. In the fourth step, we find the desired eigenvalues. So we have set the desired closed loop poles, which are the desired eigenvalues. And from those desired eigenvalues, from PP1 to PPN, we find the desired characteristic equation. So we multiply them, and from that we find this desired characteristic equation. This is the characteristic equation that we want it to be like this. While this one is the characteristic equation of the original system before any controller. So this is the old characteristic equation of matrix A for the original system, while this new one characteristic equation, this new one is the desired characteristic equation after using the controller, state controller gain matrix. Okay, and from that desired characteristic equation, we find the values of all DPs, desired coefficients, DP, desired pole placement. Okay, and finally we find the state gain feedback matrix according to this equation. Okay, those are the difference between the coefficients of the desired and the original system, and finally we multiply it by T inverse, which we calculate in the previous step here. So this is the first design method that is based on the transformation matrix. Now we will go to the second method based on direct substitution. So in the first step, always we check the controllability. If they are completely complete state controllable, proceed. If it is not, stop. So here, as I mentioned, we have A minus BK is the new system, the new characteristic equation, or the new eigenvalues. So we want to determine this Si minus A plus BK, okay, and it will be a function of the K matrix. So this is Si, this is minus A, okay, and here B, and here K. So finally we will get this matrix, this lengthy matrix, and we find the determinant of this matrix. We find the determinant of this matrix. And in the third step, we find the desired characteristic equation based on the desired location of PPs from PP1 to the PPN that we set. These poles we set, we specify. Okay, and from that we have this desired characteristic equation with coefficients dp0 till dpn minus 1. And then the final step is to equate the equation, the characteristic equation that we get from this with the characteristic equation that we get with this. So here we will equate the two characteristic equations. This is the characteristic equation that we will get from here, the determinant of this, and this is from the desired from this step. We will equate both of them, and we will determine in the fifth step the gain matrix K based on equating the coefficients of similar powers of both sides of the equation. Okay, so we will generate a system of n. The dimension of the system will be n-dimensional, and we solve it and we find the unknown values for K from K1 till Kn. And this method is convenient for low order systems. N is less than or equal to 3. And if it is larger, it will become very time consuming. And if the system is not completely state controllable, then K cannot be determined because no solution exists. So this is the second method of determining the state feedback gain matrix. The third method is based on Ackermann formula. And always we start with the controllability matrix, and if it is completely state controllable, proceed. If it is not, stop. The second step, we find the desired characteristic equation based on PPs, which is this one I have discussed before. And in the third step, we find a new matrix that is, its name is phi A. Phi A. This phi A, how can we get it? It's based on the desired characteristic equation. This one. It's based on this desired characteristic equation. But we get it by replacing each s in this characteristic equation by matrix A. So each s in the desired characteristic equation, this one, each s is replaced by matrix A. Okay? And if we replace it, we will get this phi A. So s to the power L will be A to the power N. And we continue till this term, dp1a. And finally, we will reach to this one. This is very important. Here it's dp0. We cannot add dp0 because it will be scalar. So we should multiply it by the identity matrix. In is the identity matrix of size n. We multiply the last term with in. And finally, we find the gain matrix using this formula. K is equal to a vector which is all zeros except the last one is unity, multiplied by QC inverse multiplied by phi A. And phi A is this matrix. So these are the three methods for determining the state feedback gain matrix. Okay, now in the three design methods, we assume that we have set the values of the desired closed loop poles. Okay, so the selection of the desired closed loop poles we specify from PP1 till PPN. So how to specify those PPs from PP1 to PPN? There are two methods. The first method is based on a selection of dominant pair of closed loop poles based on zeta and omega n. And this method has the following steps. In the initial phase, it will be given maximum overshoot and settling time. And from the equations of maximum overshoot and settling time, we will get this zeta. We will get the value of zeta and we will get the value of omega n from this equation and from one of those two equations. Okay, the next step is after that we specify the value of omega n and zeta. We will find the desired location or the location of the desired closed loop poles based on this equation which you know. And finally, so in this step, we have specified a pair of dominant closed loop poles. So assume that our system has n poles. Okay. So assume that this is the real axis, and this is the imaginary axis. So assume that we have specified here and here, these are the desired closed loop poles based on zeta and omega n, which we calculate based on MP and TS. Okay, so the rest, those are 2. There's left n minus 2 poles. How to specify them? Okay, the way to specify them is that we should find the real part of those dominant closed loop poles, and we should have the real part of those non-dominant n minus 2 at least 4 times the value of the real part of this pair of dominant closed loop poles. So assume that the real part of this pole, this closed loop poles desired is alpha. Then we might place the remaining, whether they might be real roots or complex conjugate roots, and the real part at least it should be for alpha. Okay, it might be less than, it might be further to the left, okay, but it should not be closer, because if it is closer they will be non-dominant. Those pair will be non-dominant. So we want to guarantee the dominance, and to guarantee the dominance, the ratio of the real part of the non-dominant should be at least 4 times the value of the real part for the dominant. So I wish that everything is clear, and this we have discussed in the control course, dominance and non-dominance. So in the third step, we choose the rest of the poles which are n minus 2 such that they are non-dominant. Okay, regarding the real part, while their imaginary part we might keep it the same. So this means that the real part of the rest of the closed loop poles, they should be at least 4 times the real part of the dominant. Okay, while the imaginary is kept the same, or we might select a complete set or partial set of real roots without imaginary part. But all of them, they should have at least 4 times the real part of the dominant. Okay, and while doing so, we should not place the dominant far away from the j omega axis. Then the system will be very, very fast, and we should avoid this. So this is the first scenario of selection PP1, the desired closed loop poles, till PPN. The second scenario, which we cover at the end of this chapter, is based on linear quadratic regulator based on optimal control technique. So in this scenario, we don't specify them exactly. We specify an objective function, this one. And this objective function should be, or cost function should be, minimized. So the poles are selected such that they should minimize an objective function which is given in this equation. And according to this equation, the roots will be, or the desired closed loop poles will be selected, not directly, indirectly. Okay, so let us take examples. Here we have a system of 3 by 3. Okay, and it's given in the CCF format, and we want to use state feedback control U is equal to minus kx, and the desired closed loop poles, they are 3. Since the system matrix is 3 by 3, they are 3 eigenvalues or desired closed loop poles. Look at those pair of dominant closed loop poles. The real part is minus 2, while the third one should be non-dominant. The third is non-dominant. Its real part is 5 times the minus 2. So the dominance is guaranteed. And this is the block diagram of the regulator that we discussed before. So what's required? We should design the matrix G based on the 3 methods that we discussed. The first one is the similarity transformation. So we find the QC, and we find its rank, its full rank. The system is completely state controllable, and we can proceed. After that, we find Si minus A, and this is the characteristic equation of the original system. And from that, we find A0, A1, A2. And this, since the system here is given in CCF form here. Okay, so t is equal to I, since it's already in CCF. So we will continue the solution. So we go to the fourth step, the desired characteristic equation. We multiply s minus p1, s minus p2, s minus p3, and we get this equation, and we equate it to dp's, and from that we get the dp's. And the gain matrix is, as I discussed in the previous method, is the difference between the coefficients, the respective coefficients between the desired and the original multiplied by t inverse, and t inverse in our case is I, so k is equal to this vector. So now we will go to the direct substitution method. Okay, and again the system is completely state controllable, so we can proceed. So the gain matrix will be, or the state feedback gain matrix is k1, k2, k3, and we find Si minus A plus Bk. So this is Si minus A plus Bk, and we will finally get this determinant, this characteristic equation of the desired location. And the desired location is S minus P1, S minus P2, S minus P3 multiplied with this, we will get this. So we will equate this equation with this equation. We will equate both of them. So this is the complete numerical value, and this is the characteristic that contains the case. So from this we will get those three equations, and from that we will get this k, and the k here is equal to the k which is in the first method. Okay, the design, the state feedback gain matrix should be the same regardless of the method. So the final method is the Ackermann formula according to this formula, and if we proceed, so the desired characteristic equation, as we say, we will calculate it like this, and we will replace each S by matrix A in this desired characteristic equation according to this method. So we find, if you see, this is, we replace each S by A, and the final term, this one, we multiply it by I in order to be added to the matrix. So finally, we will get this phi A, and this is the QC, and this is the QC inverse, and finally we will have this formula, and if we multiply we will get this. So these are the figures here, they are the responses of the respective states. Here state 1, okay, and this one is without state feedback, while the solid line is with feedback. As we see, it's much faster, and it's very good response for X1. And for X2 also, this is without state feedback, and this is the blue one with feedback. So again, it's much faster and much better. And if you go to the third state, this is with feedback and this is without feedback, and the design is over. So we will go in the next example to the inverted pendulum example. This is a realistic example, okay, and this is its modeling process. It should be covered in the modeling and simulation course. So it's a system of 4x4 here with one input and two outputs, okay, and what's written? It's written that the desired closed loop poles, this is a pair of dominant with real part of -4, while the non-dominant, they are real roots and they are 5 times the real part of this. And we want to find the value of the state gain feedback matrix. So QC, we find it in the first step for all cases, and since QC, the determinant is non-zero, then the rank is full rank for QC, and the system is completely state controllable, and we can perform this pole placement technique. So the first method is transformation method. So we find the characteristic equation of the original system. This is the characteristic equation, and from that we find the corresponding A's, and we find the transformation matrix. Finally we will get this T. I will not go through details. This is, we have taken the similarity transformation. This will convert the system from any given thing to CCF, okay, and the desired characteristic equation S minus PP1, S minus PP2, S minus PP3, S minus PP4, and we will get this, and from that we will find the dPs. And finally, this is the formula for calculating the K. Okay, if we plug in all of the values, we will reach to this value. K is equal to this value. Okay, and the third method is the Ackermann method, and this is the design rule. Okay, the desired characteristic equation is this, and phi A is based on the desired characteristic equation. Finally, phi A is this, and if we proceed, QC is this matrix, the inverse is calculated like this, and finally K is calculated according to the Ackermann formula. Finally, we will reach to this value, which is again the same as the previous values of K which we discussed. And these are the responses of the 4 states. We have 4 states. This is x1, x2, x3, x4. And this is another example in electric circuits. This is the DC-DC converter, which might be boost converter or buck converter. This boost, this buck converter, and it's a 2x2 system with single input, single output. So we check the controllability. QC will be 2x2, and it's for rank, so the system is completely state controllable. And K will be consisting of 2 values, K1, K2, since we have 2 states. And we find it, okay, using the direct substitution method, Si minus A plus Bk, the determinant, and we will get this value. And the desired one, if we go back to the problem statement, it's written here that we design a state feedback gain matrix such that the overshoot is 20% and the settling time is 0.5. So here we have 2 states, and we have no more states. From those 2 states can be determined, or the closed loop poles for the dominant case, they can be determined directly from the overshoot and the settling time. So from this overshoot and settling time value, okay, here overshoot is 20% and settling time is 1.5. So we will find omega n and zeta from the previous equations, and this is the desired characteristic equation, and we will equate both equations. From that we find the values of K1, K2, and this is the gain matrix, and these are the responses of the 2 states due to initial conditions. Here we have the initial conditions here. Okay, so the blue is without state feedback, without controller, and the red is with gain feedback. It's smooth, it's fast, and also here the same thing with the second state, which is the capacitor voltage. And if you pay attention, we said that the system in all of the previous examples we have 0 input, so it's due to initial conditions. And as we discussed in the system stabilities, whether in the conventional course or in the current course, if we excite any stable system by bounded initial condition, the response should go to 0 as the time go to infinity. And if you pay attention to here, it's approaching 0, the state, the first state, and also the second state is approaching 0. So this is a stable system. So in this way we have covered the pole placement technique, and in the next lecture we will cover the designer of observer in the next lecture. Thank you, and I wish that you understand everything in this lecture. Thank you.